Welcome to BADM A724 Quantitative Methods and Business Analytics. This is Lecture 7. I'm your instructor, Dr. Frank Tian Shea. In this lecture, we'll talk about the continuous distribution, probability distribution, uniform continuous distribution, normal distribution, standard normal distribution, normal approximation to the binomial, and the normal approximation to the Poisson distribution. Okay. First, for continuous variables, remember when we talked about the discrete variables last time, each value of discrete variable x has its own probability, or px, right? Px for variable x. But for continuous variables, the events are not at each discrete points, but are intervals, and probabilities are areas underneath smooth curves. So a single point has no probability in this case. Like this chart shows, for discrete variables, the probability is defined at each point. 0, 1, 2, 3, 4, 5, for example. And then for continuous variable, the probabilities are defined over an interval. Right? It's not just on each individual point. Okay? So for PDF and for probability distribution functions, for continuous PDF is denoted by fx, or the function, the curve fx, and must be non-negative, meaning the probabilities cannot be a negative, has to be larger than 0, a positive number. But the total area under the curve must be 1. Right? This chart on the right shows that the miles per hour, that's how fast people drive, on the highway, interstate, the average speed is probably something around 75 miles per hour, right? Even though speed limit may be 70, but we all know that most people drive at 75. Right? So if you plot the speed people drive at on interstate highways and the probabilities, you'll find that more people, or most people, are driving at a speed of 75 miles per hour. So that corresponds to the highest point in the curve. And it's probably normally distributed, meaning there are fewer people driving under 75, there are fewer people driving over 75, right? And they could be driving as high as 90 miles per hour, waiting for a ticket to come in, or driving too slow to under 660 or below, then you're probably becoming a hazard to others as well. But the overall is a continuous function, right? And the probabilities under the curve, total areas under the curve, under this red line curve, normal curve, is 1. Why is it 1? Because that covers all the possibilities. This red line does not touch the x-axis, because it just approaches x-axis infinitely on both sides, this side and this side. And the total area is 1 because it covers all the possible speeds people can have. At least is 0 miles per hour. And the highest, I don't know, the highest, someone could be crazy and driving at 200 miles per hour. But all the possibilities are included. So the total area must be 1 under the curve, the whole area here. Okay, that's the total probability. The mean, variance, and the shape depend on the PDF parameters. Okay? And the chart here reviews the shape of the distribution. What about continuous distribution function? For continuous distribution function, remember we start from the lowest point and keep adding probabilities, and it'll grow up, grow, and keep going up until it reaches 1. That's the cumulative distribution function. is denoted as fx, capital Fx, and shows that the probability of x is less than or equal to small x. That's the cumulative proportion of scores in this case. Okay? And it's useful, very useful for finding probabilities. Okay? As I said, the probabilities in continuous function or continuous distribution functions are smooth curves under the curve. Right? You cannot say what's the probability at say a point A or point B, but you can also only say or define the probability under the curve between A and B. The shaded gray area as a probability. Okay? Unlike discrete distributions, the area at any single point is 0. Okay? And the entire area under the curve, PDF, must be 1. Okay? And the mean is the balance point of the distribution, somewhere here, the balance point of the distribution. First, now let's talk about the uniform continuous distribution. That's the simplest form of continuous distribution. In this case, the characteristic of the uniform distribution is that if x is a random variable that is uniformly distributed between A and B, the PDF has a constant height, meaning it is a uniform distribution. So between the variable x can only take the value, any value between point A and point B. But anywhere between A and B, its probability is constant at 1 over B minus A. So, and therefore is the horizontal straight line. And so the curve is just like this red rectangle. Okay? Now, why is the height 1 over B minus A? You may wonder. Right? It's because the whole area is 1, right? The whole area is 1. And how do you get the area of rectangle? It's the base times its height, right? And the base, of course, we know between A and B, the base is B minus A, right? And then in order for total area to be height times base equals 1, you have to have the height as 1 over B minus A. Then multiply that by B minus A, you get an area of 1. Okay? So we can denote this as UAB, that's uniform distribution between A and B. The area is the base times the height. B minus A is the base, this line here. And the height is 1 over B minus A, that's this line here. And B minus A point cancels each other, and then you have area of 1. Okay. These are the characteristics of the uniform distribution. A is the lower limit, B is the upper limit. The probability distribution function is this, 1 over B minus A. The CDF is x minus A over B minus A. We're not getting into details mathematically as to why, but for this class, for the purpose of this class, we just need to know, what are the formulas, equations to use. Okay? The domain is between A and B. The mean is simple, A plus B divided by 2, the average of the 2. This is standard deviation. Okay? The shape of that is symmetric with no mode. Okay? And the random data in Excel, you can use this to get random data. Right? It's used as a conservative what-if benchmark of uniform distribution. Okay? And the CDF of a uniform distribution, it increases linearly to 1. Right? It starts from 0. At point A, it starts to go up, increase, and keep going up in a straight line until it reaches point B, and then at 1.0 reach 1.0 and become flat line again. So that's the CDF for a uniform distribution. Okay. So the CDF formula is x minus A over B minus A. Let's use this uniform distribution as an example to work on the problem, anesthesia effectiveness problem. Many of you, most of us probably have had the tooth extracted over the years, right? An oral surgeon injects a painkiller prior to extracting a tooth. Yeah. Given the varying characteristic of patients, the dentist views the time for anesthesia to take effect as a uniform random variable that takes between 15 minutes and 30 minutes. Well, this is the uniform random variable, and it could take between 15 and 30 minutes. So for someone, maybe a big guy, for older person, a small, weaker person, it may take 15 minutes to numb the person down. And for a strong, big guy, maybe it takes 30 minutes to get him numbed, right? But the chances of anyone taking whatever time it takes to be numbed, is a random variable, and it can only be between 15 and 30 minutes. Nobody takes less than 15 minutes, to be numbed, and nobody takes more than 30 minutes to be numbed. Okay, so for this variable x, it's U1530, uniform distribution between 15 and 30. Okay, A is 15 and B is 30. Now, what will be the mean and standard deviation then? Mean will be A plus B over 2, or 15 plus 30 over 2, 22 minutes, 22 and a half minutes. And that's the average time that it takes for people to become numbed. Then the surgeon will come and take out your tooth. And then the standard deviation of that is B minus A squared over 12, and the square root of that, the radical of that, and you calculate that, carry out the calculation, you get 4.33 minutes. Okay? Now, let's find out what would be the probability that anesthetic would take between 20 and 25 minutes. Yeah. In other words, what's the chances? What are the chances that someone coming in, the anesthetics will take between 20 and 25 minutes to take effect, right? So in other words, what's the P probability of X between C and D? C and D is 20 and 25. So, and from the equation we have, P X between C and D is D minus C over B minus A. So therefore, Px between 20 and 25 will equal 25 minus 20, that's D minus C, over B minus A, 30 minus 15, or that's 5 over 15, or 0.33, or 33.33%. So roughly, that's 1/3, right? So it's 1/3 of people, right? Between 20 and 25, that's about 1/3 of people will take between 20 and 25 minutes to get numbed, right? But we probably, this is of course this is an easy case, right? And it's very straightforward. But if you look at this, we know between 15 and 30, that's 15 minutes total, right? 15 minutes total, you take 5 minutes in the middle, right? And there's 5 minutes here between 15 and 20, another 5 minutes between 25 and 30. So basically, this must be 1/3, and this must be another third, and another third. So, and we don't even need a calculation now. We know that between the probability that anesthetic will take effect between 15 and 20 minutes is also 33%. Between 25 and 30 minutes, also 33%. What about between 15 and 25 minutes? 33, that's 66%, etc. Okay. Next, let's talk about the normal distribution. That's probably one of the most widely known and used, the probability distribution of all. And you probably have heard a lot about this. It's called normal distribution, or called a Gaussian distribution, or called a bell-shaped curve. It's a distribution after a German mathematician, Carl Gauss, in 1777 to 1855. He's a genius in mathematics, and he actually found this beautiful curve and the equation for that, right? We're not getting into the how he got that and the miracle, the interesting part of the equation, right? The normal distribution is defined by two parameters we already know, and that's mu and sigma. Mu is the mean of the population, and sigma is the standard deviation of the population. So the normal distribution is denoted as N, capital N, normal distribution, mu and sigma. In other words, you only need to know two parameters, the mean of the population and the standard deviation of the population. Then you can construct the normal distribution, that beautiful bell curve. Okay? And the domain is negative infinity and plus infinity. It's a continuous scale, so the curve itself never touches the x-axis, but approaching it infinitely. Okay? Almost all area under the normal curve is included in the range of minus 3 sigma and plus 3 sigma. You probably heard about for those of you in business already, you probably heard about the 6 sigma series, right? Theories about quality management. They're talking about the 6 sigma plus and below the mean. Now that's a very large area, right? But for most cases, in most instances, between 3 sigma plus and minus, we cover most of everything. Okay? And the normal curve is symmetric and unimodal about the mean. Okay? And the characteristic of normal distribution, as we just said, the mu is mean of population, sigma standard deviation of population. This is the equation for that, probability distribution function of that. Right? This is sigma here. The pi is just the pi, the 3.1415926. And E is the base of natural logarithm, E, 2.718, and etc. Right? The domain is minus infinity to plus infinity. Mean is mu, of course. Standard deviation is sigma. Symmetric, bell-shaped. This the random data in Excel. You can use this to get that. Is used as a benchmark to compare other distributions. Very widely used. Okay. The characteristic of normal distribution. Normal PDF reaches a maximum at mu and has a point of inflection at mu plus minus sigma. Right? At mu, the mean here, that's its maximum point. Right here is also the mode. Okay. It's bell-shaped curve. This point here, mu minus 1 sigma over here on this side, and mu plus 1 sigma on this side. That's the point of inflection. And you can see that the curve here, before this point, it kind of curves like this, right? And above this point, it goes like this. So it's convex and concave, right? So that's why it's called the inflection point. All normal distributions have the same shape but differ in the axis scales. So it could be skinnier, taller, like this. It could be fatter and wider, like this. Okay. Normal CDF, though, is coming from infinity, all the way going up, and it reaches 1.0. Okay. And with the inflection point here at mu. Then we use the standard normal distribution. Remember we talked about standardization of data, z-score, right? And because things in nature or in society, in business, the distribution of data, they could take any shape. That they can all be normal distribution. So tall and skinny, or fat and low, right? And of course, there's a normal one, the bell curve, the normal standard bell curve. So if we can standardize it, that means then we can use tables to do simple, easy calculations and estimations. So Since for every value of mu and sigma there's a different normal distribution, we can transform a normal random variable to a standard normal distribution. And after we do the transformation, the mu will be 0 and sigma will be 1. And we can then use a standardized table to find the probability. And how do we do the transformation? Just like we did before, z transformation, z scores. Z equals x minus mu over sigma. Okay. And then for after transformation, the normal distribution will become a standard normal distribution with the mu of 0 and the standard deviation of 1, denoted as capital N 0, 1. Okay. And the characteristic of the standard normal is simpler than the normal distribution. Mean of 0, standard deviation 1, domain still in infinity, minus, plus, minus, right? And the z, that's a PDF. This is how z is defined. Okay? It's a symmetric bell-shaped curve that we see the most often. Okay? Standard normal PDF reaches a maximum at 0.0 and has a point of inflection at 1. Remember, 1 sigma, in this case the sigma is 1, so at minus 1 and plus 1, that's the inflection point. And the shape is unaffected by the transformation. It's still bell-shaped curve. And the standard normal CDF is like this, and the inflection point is at 0. Okay? Remember, there's 0 here. Characteristic of standard normal. Common scale from -3 to +3 is used. That's -3 standard deviation and +3 standard deviation. The entire area under the curve is still 1 unity. The probability of event P between Z1 and Z2 is the definite integral of Fc. However, standard normal tables of Excel functions can be used to find desired probabilities. In your book, you go to Appendix C1, and you will be able to find the areas under the curve from 0 to Z. Right? Look at now it's good time to pause and go to your textbook, Appendix C1, to get yourself familiarized with Appendix C1. Okay? For example, in C1 you see this chart, you see the table. Now, what is the probability of Z between 0 and the 1.96? From 0 here to 1.96. We know the whole area under the curve is 1. Now, what is the P probability of between 0 and 1.96? If you go to Appendix C1, you find that this area, it's a shaded area under the curve, is 0.4750. Now this number is important. We'll get to that later on. Okay? It's 0.4750. Okay? That's a probability. In other words, in this distribution, the chances were 0.4750, where almost 50% of the observations will lie between 0 and almost 2 standard deviations. Normal areas from the C1. Now, what will be the area between minus 1.96 and plus 1.96? We just look at between 0 and 1.96, right? What about the area between minus 1.96 and plus 1.96? And remember, it's symmetrical, right? So due to symmetry, P between Z larger than minus 1.96, it should be the same as PZ less than 1.96. So this area here under the curve should be the same as this. So together, between minus 1.9 and plus 1.96, that's what we have. You add 0.4752, and 0.475 plus another 0.475, you get 0.95. Does this ring a bell? Okay. Remember the empirical rules we talked about in previous lectures? Okay? We talked about the roughly between 2 sigma plus 2 and minus 2, the probability is 95%. That's where this is. This is where that's coming from. Okay, between standard deviations 1.96 and the minus 1.96, you should cover 95% of all observations. Okay, 0.95. Okay. So that's that. So 95% of area under the curve. Yep, as we just said. The basis of the empirical rule. Now let's go back and recall the empirical rule we talked about. We were talking about the approximately 68% of the area under the curve is between +1 and -1 sigma. +1 and -1. It's actually 68.34%, right? And between +2 and -2 is actually 95.44. We use 1.96, plus and minus to get 95%. If it's between 2 and -2, it's a little over 95%, right? So it's actually 95.44% between +2 and -2, right? And between 3 sigma, 3 plus 3 and -3, there should be 99.73% right here of the curve. That's why we say in most cases and most circumstances, 99.7% of the observations will be between 3 sigma. Right? If you are outside 3 sigma, that's really an outlier. Okay. Okay, let's continue. In the back of end of your book, there's also a table C2, Appendix C2. And C2 allows you to find the area under the curve from left of Z, kind of similar to in Excel, towards in Excel. For example, what would be the probability to the left of 1.96? It's 0.1.96. In other words, what's the area under the curve of the shaded area here? The curve. And that's where you can go to table C2 or appendix C2 to find that. And that should be 0.9750. Look at your book, you should see that number. Okay? And then what will be the area to the left of minus 1.96? Or that is Z less than minus 1.96. In the book, you'll find that is 0.0250. There's a little shaded area here. And then what is the area between minus 1.96 and plus 1.96? We already know is 0.95%. Right? In fact, if you, from this chart here, 1.9750, if you take out this little section here, right, on this side, it should give you use this, subtract back this, you get 0.95%. Right? Table C1 and C2 are actually talking about exactly the same thing. It's just from different approaches, different ways. One is to the left side of that, and the other is, if you go back, it's actually between 0 and that at a given point. They're talking about the same thing. Okay. Yeah. So as I said, appendix C1 and C2 yield identical results. Use whichever table is easiest for you. Okay. And also you can use the C1 and C2 to find the Z score for a given area. Right? Appendix C1 and C2 can be used to find the Z values corresponding to a given probability. That's you go to the main body of the probabilities, find a number that corresponds to the probability, if that is known, and then you can find the corresponding Z score or Z value. For example, what Z value defines the top 1% of a normal distribution? Top 1% of distribution. This implies that if the top 1%, that implies that 49% of the area lies between 0 and Z, right? That's why it's 49%, right? And which gives a Z of 2.33 by looking for an area of 0.4900 in appendix C1. Once you go to table C1, appendix C1, look for the probability of 0.49, you will find the Z score of 2.33. Okay. Let's take an example here. Finding errors by using standard variables. Right? Let's suppose John took an economics exam and scored 86 points. The class average is 75, with a standard deviation of 7. What percentile is John in? That is, to find the probability of X less than 86, right? So dash is the percentile John is standing at, because he scored 86 out of the whole class when the average is 75. So to do that, all you have to do is just calculate the Z score for John, which is X minus mu divided by sigma, 86 minus 75 divided by 7, or 11 divided over 7. That's 1.57. So that's John's Z score. It's 1.57 standard deviations above the mean. And then you go to the book, go to table C2. This time you can go to C2, right? For P X less than 86%, 86, I'm sorry, not 86, not percent, or Z score less than 1.57, somewhere over here, right? The probability, the area is 0.9418. In other words, if this is 1.57, just a little bit to the right of 1.5 between 1 and 2, and the total area to the left of that is 0.9418, and that is saying that the John is approximately in the 94th percentile, or his score is higher than 94% of his class. Okay? You can also use Excel, Minitab, TI calculator, 8384 to compute these probabilities directly. They all should give you the same result. Okay? Normal approximations. Since the normal distribution is so easy to use, so widely used, sometimes other probability distributions are harder and difficult to use. And then we normally try to use normal distributions to approximate other distributions. So when is approximation needed? Binomial distribution. Remember binomial we talked about? Yeah. Binomial probabilities are difficult to calculate when n is large, but we can use normal approximation to the binomial. As n becomes large, the number of observations becomes larger and larger. The binomial bars become more and more continuous and smooth. Right? This is the case when n is, I believe, is the bars, is let's see here, n is 5 and 4. Wait a minute. I can't see it here. Yeah, n is 4, right? And this is distribution like this, right? And this the skewness and kurtosis, mean, and standard deviations, right? If n becomes 8, this is what you get. Right? If n is 16, this is what you get. You can see the binomial distribution, is more and more like a continuous distribution, comes up, becoming like a smooth bell curve. Therefore, so if n is large enough, we can use normal distribution to estimate binomial distribution. Okay. So when is approximation needed? The rule of thumb here is if n times pi is equal to or larger than 10, and n times 1 minus pi equals or is larger than 10, then it's appropriate to use normal approximation to the binomial. Right? In this case, the binomial mean of standard deviation will be equal to the normal mean and standard deviation. So for binomial, the mean will be n times pi. Remember, in previous slides, you see that's the n times pi is a mean for binomial, and n times pi times 1 minus pi, and the square root of that is give you the standard deviation. And if you know the mean and standard deviations, then you can calculate the binomial just as if you were calculating the normal distribution. So you can use that as approximation. Okay. Let's take an example here for coin flipping. Right? If we were to flip a coin, n equals 32 times. Remember, coin flipping, 2 outcomes, that's a Bernoulli experiment. If you repeat that many times, it becomes a binomial. Right? So if we were to flip a coin, n equal to 32 times, and pi is 0.5, that we know the probability 0.5, as that there's an equal chance, 0.5 chance you get a head or a tail. Are the requirements for normal approximation to the binomial met? Let's find out. N times pi is 32 times 0.5 is 16. N times 1 minus pi, 32 minus 1 minus 0.5 is 16. So both are larger than 10. So a normal approximation can be used in this case. Then when you know the pi, you can calculate the mean and standard deviation. You can use the normal table, appendix C1 and C2 for the same calculation. When translating a discrete scale into a continuous scale, care must be taken about individual points. Careful with that. Okay? For example, find the probability of more than 17 heads in 32 flips of a fair coin. You flip a coin 32 times. Yeah. What's the probability of more than 17 heads? Right? Then this can be written as px larger than equal to 18. Right? So, but more than 17 actually falls between 17 and 18, right? So if you use 18, that's a little bit wrong because 17 and a half is also larger than 17. So we need to do some adjustment here. Okay? So more than 17 is actually between 17 and 18. Therefore, we can use 17.5, right? 17.5. And we call that continuity correction. Right? Since the cutoff point for more than 17 is halfway between 17 and 18, we add 0.5 to the lower limit and use px larger than 17.5 to calculate the probability. So it's more precise. This is called continuity correction. At this point, the problem can be completed as any normal distribution problem. Okay? Done. As a rule, continuity correction. This table shows some events and their cutoff point for normal approximation. For example, if you want to find at least 17, okay, at least 17, we should use on the curve here between this 17 and higher, right? We probably should use 16 and a half as cutoff, right? More than 15, we probably should use 15.5. Fewer than 19, we probably should use 18.5, etc. Okay. Normal approximation to Poisson distribution. Remember Poisson distribution we talked about before? Poisson distribution is arrivals in a given time. Remember, arrival to a train station at a given time during the day, etc. Right? And can we use normal distribution to approximate Poisson distribution? Yes, we can. Right? And this one, remember, this is Poisson, and some people call it poison. They come close enough, right? So when is approximation needed? The normal approximation to the Poisson works best when lambda is large. That is, when lambda exceeds the value in Appendix B. Look at your book in Appendix B, and then when lambda is large, you can use normal distribution to approximate Poisson. You can set the normal mu and sigma equal to the Poisson mean and standard deviation. And we know in Poisson distribution, the mean of Poisson distribution is just lambda, so mu equals lambda. And standard deviation in Poisson is the square root of lambda, so the standard deviation is square root of lambda. Then you have mu, you have sigma, you can just calculate as normal. Okay? Let's take an example. Right? On Wednesdays, for the utility bills, on Wednesdays between 10 a.m. and noon, customer billing inquiries arrive at a mean rate of 42 inquiries per hour at Consumers Energy Company, electricity company. What is the probability of receiving more than 50 calls during that time period? Right? As soon as you see that the arrival in a given period of time, that's the Poisson distribution. So in this case, lambda is 42. 42 inquiries per hour. Right? Lambda 42, if you go to Poisson table, they don't have it because it's too big to use the Poisson table. But we can use normal distribution to approximate it. In this case, the mu for normal distributions, mu is lambda equals 42. Right? And sigma standard deviation is square root of lambda is square root of 42 is 6.48. You have mu, you have lambda, then you can do the calculation. Okay? And also to find the probability of larger than more than 50 calls, remember the continuity correction? Right? We should use a cutoff point halfway between 50 and 51. In other words, we can use 50.1, right? And then use that to calculate z-score, and then go to C1 or C2 to find probability, we can solve the problem. At this point, the problem can be completed as any normal distribution problem. Okay? I think that is the end of this lecture. I'll see you next time.